All right, here we go. Day two. Day two is all about two-sided limits. Today's objective is to evaluate and prove the existence of two-sided limits, extending our knowledge from day one of one-sided limits. So we'll see what I mean by two-sided in just a moment. We'll start off with a quick review. Something you might have seen on Delta Math last night is to be asked about the behavior of this function as we approach some value, let's say -3. And so the first thing I'm going to do, these are all like annotations that you can do. First thing I'm going to do is draw a dashed line down through x equals 3. That's just going to help me visualize, -3. That's going to help me visualize what's happening at -3 to answer these questions. First question is just what is f of -3, meaning what is y when x is -3. And I know that that closed filled in dot, right? That's the one that counts. So I just look and I say, I like draw over in my head what is the y value at that point, and it's also -3. So f of -3 is -3. Now, what we learned, our first like actual calculus lesson, was we talked about this idea of a limit. We learned limit notation, and we learned that this next statement says the limit of f of x as x approaches -3 from the left. So you have to remember that that's what that little minus sign that looks like an exponent, that means we're approaching from the left. So we have to actually see what is the behavior of this function. Now, a recommendation I have is to actually go ahead and label these things. When you're doing this on your own, literally use your fingers, draw up these, and drag your fingers along from these directions to make this easy. So I put my finger somewhere to the left of -3. Let's start here at like -9, -9. Now y is -8, or sorry, -9, 9. So 9, now y is 8, now y is 7, 6, 5, 4, 3, now y is 2, now y is 1, now y is 0, we're getting close, now y is -1, now y is -2. As we follow this function, in this case it's the same as f of -3. We're approaching the same value that we actually wind up at. So this one is just also -3. But with limits, right, we can have from either direction, and this little plus sign here means from the right. So you have to pick a point on the function that's to the right of -3, to the right of our dashed line, and follow it. So you can literally start anywhere you want. Let's say we start here. This is to the right, so we go y is 4, y is 2, y is 0, now -2, -4, -7, -6, -4, -2, -1, 0, 1, 1.5, 1.7, 1.8, 1.9, 1.99, 1.99999, 1.9999999. You're getting closer and closer and closer to 2. It does not matter that at f of -3, you jump down to -3. That's irrelevant. The limit from the right is 2. It's what y value are we getting closer and closer and closer to, which you could see in a table of values, that we're going to get closer and closer and closer and closer. Now, what we're going to talk about today is what happens if you don't have a left or a right symbol there. This is what we would call a two-sided limit, or maybe just refer to it as a limit. If you don't say left or right-sided, it just means the two-sided limit. So this here says, what is the limit of f of x as x approaches -3? Full stop. And what you're looking for here is, are the left-hand and right-hand limits the same? In this case, they're not. From the left, y is getting closer to -3. From the right, y is getting closer to 2. We would say that this limit does not exist, DNE. And we would say that that limit does not exist because that is the definition of a two-sided limit. So here we go to what we're going to call one of our first existence theorems of calculus, the limit existence theorem. And the limit existence theorem says the limit of f of x as x approaches a, so a is some number and x is the input variable, exists if and only if. And now if and only if is one of my favorite abbreviations. You're going to see that sometimes as IFF. Means if and only if. Mean this is only true if the following statement is true, and if the following statement is true, that's that necessarily means that the limit's going to exist. The limit of f of x as x approaches a exists if and only if the limit of f of x as x approaches a from the left is equal to the limit of f of x as x approaches a from the right. If the left-hand limit and the right-hand limit are the same, the two-sided limit exists, and it is equal to those two things. So let's see what that would look like in practice. Let's say we have this function here on the right, and I ask you what the limit is of f of x as x approaches negative 1. So I go and I draw my dashed line, I look at what's happening at negative 1. And it turns out that even though f of negative 1 is undefined, the limit as x approaches negative 1 is negative 2. And if I asked you to justify that statement, you'd say, because the limit as x approaches negative 1 from the left of f of x equals the limit as x approaches negative 1 from the right of f of x equals 2. That would be a way to prove that the limit as x approaches negative 1 is negative 2. Missed my negative 2 the second time around there. Let me make that a little bit cleaner for the notes. Okay, so it also applies even if f of x is some different number. So let's look at this next one, the limit of f of x as x approaches positive 2. Draw my line down the paper. My limit from the left, I am approaching, getting closer to a y value of negative 2. My limit from the right, getting closer to a y value of negative 2. It does not matter. It does not matter. Even though f of 2 is negative 3 because of that closed circle, the limit is still negative 2 because the limit is just asking what number are you approaching, not what number you actually finally wind up with. So here's the key point. F of c does not have to exist. So that was the first case. It was just the function was purely undefined at f of negative 1, or be equal to the limit as x approaches c of f of x. Those can be different numbers. Okay? So now we're going to look at a few more things. I'm just going to give you 3 quick examples of reasons that limits fail to exist. So reasons you might not have a limit. First, let's say the case we've already covered, the limit as x approaches negative a does not equal the limit as x approaches a from the left does not equal the limit as x approaches a from the right. So if I asked you what the limit was as x approaches 1, it would be does not exist, because from the left the limit is 1, and from the right the limit is 3. We're getting closer and closer and closer to 3. The same would be true at 2. As x approaches 2, the limit from the left is 3, and from the right is 2. You're approaching different numbers. Another example of why limits would fail to exist would be limits at infinity. And so in this case, if we look at what's happening at x is equal to 3, the limit as x approaches 3 from the left is negative infinity. The limit as x approaches 3 from the right is positive infinity. Now some textbooks will even say if we had, let's say we had the graph of y equals, let's say we had y equals 1 over x squared. So as x gets closer to 0, right, you're dividing by smaller and smaller numbers, y is going to infinity. So this graph would look something like this. You'll see this come up on Delta Math. You could describe the limit as x approaches 0 of f of x either as dne or infinity. It just depends on what textbook you look at. The example on the right is 100% dne because we're approaching different infinities, positive and negative. The one on the left, it just depends on what textbook you consult. AP will take either. You could either say the limit doesn't exist, like it's limitless, or that the limit is infinity. The last one is definitely a weird one. And it's called infinite oscillations. And so what that means is your function does not have a limit at a value, in this case at 0. So the limit of the function to the right as x approaches 0 does not exist. Because if you were to zoom in on this function, right, think about how a sine function works. If we do sine of 1 over x, we're alternating through the unit circle. And so notice this function goes up to 1, then down to -1, then up to 1, then down to -1, then up to 1, then down to -1. If you could keep zooming into this function, it would do that forever. It would keep what we call oscillating on either side of 0, positive and negative. So we would say there that the limit does not exist. It's not heading towards any number because it keeps going up to +1, down to -1, up to +1, down to -1. That we would call infinite oscillations. So a couple ones to end on. What I'm going to do is I'm going to make this in Edpuzzle, so it's going to pause and give you time to answer. Again, real big distance learning key point, like own your learning. Don't just click through and immediately go on. Like take some time, take a second to actually try each of these problems. To do them at AP pace, you want to be doing these in about 1.5 minutes. So 1.5 minutes per question. I'm going to go ahead and put this as an Edpuzzle question, pause it, do it on your own, and then we'll come back and talk about it. Okay, so what we have here, for which of the following does the limit as x approaches 4, so this is a two-sided limit, exist? Okay, so let's look at each of these graphs. Graph number 1. Okay, graph number 1, if I look at it from the left, that's totally fine. It's approaching what looks to be 3, and from the right, it's also approaching 3. It does not matter that this is a removable discontinuity. That is totally fine. It doesn't change the fact that the limit as x approaches 4 is 3. So anything that doesn't include 1 is out. That's gone, and that's gone. If you guessed right now, you'd have a 33% chance of getting this one right, which almost gets you to a 3 on the AP exam. I kid you not. We'll talk about that later. It's a hard exam, so you literally only need like a 38% to get a 3. Let's look at graph number 2. Graph number 2, same idea. We have a discontinuity here, but that actually has nothing to do with limits. The fact that f of 4 doesn't exist is fine. This limit is still going to be 4 because the limit from the left and the limit from the right are the same. So it's got to include 2. So there we go. If I was really confident, I wouldn't even have to look at 3. But just because, let's just look at it. For number 3, from the left, it looks like we're getting closer and closer and closer to 4. And from the right, it looks like we're getting closer and closer and closer to 2. So yep, 3 doesn't work. So that's the first one. Second question. Figure above shows the graph of a function. So it's this graph to the right here. Let me get that in frame. The figure shows the graph of the function f with a domain 0 to 4. Okay, which of the following statements is true? The limit of f of x as x approaches 2 from the left exists. The limit of f of x as x approaches 2 from the right exists. Or the two-sided limit as x approaches 2 exists. Take another 1.5 minutes or however long it takes you to do this problem and come back. Okay, so here we go. First up, the limit as x approaches 2 from the left. So from the left as x approaches 2, again, if it's helpful, you can put a dashed line there. We are approaching some value. All I care about is does it exist, so who cares what that actual value is? The limit as x approaches 2 from the left definitely exists. So anything that doesn't have 1 is gone. Number 2, does the limit as x approaches 2 from the right exist? And it does. There's no reason for it not to. It doesn't go to infinity. It doesn't oscillate. We're on that number, whatever that number may be, and our limit is whatever number that horizontal y value is. So it has to include 2. So here we go, and here we go. The question is just now between, does that mean the two-sided limit exists? And we just proved this. If the first-sided limit exists and the second-sided limit, if left and right limits exist and are the same, then we know that the overall two-sided limit exists. But in this case, they're different numbers, right? They have to be the same number. And in this case, since 1 is clearly higher than the other one, the two-sided limit does not exist. The answer is C, 1 and 2 only. All right. As a final challenge here, go ahead and write in words. All right, you're going to have to type this out in words in the open response. Write me a statement proving that the limit as x approaches 1 of f of x does not exist in the function to the right. So when you do this, you're going to have to write things like the limit of f of x. You're going to have to type out the word of as x approaches 1, but that's really good practice. So take 2 minutes to write me a statement proving that the limit does not exist as x approaches 1, and then come back to see. I'll do it in actual mathematical notation. All right, so here we go. What I've got here, from the left, so I would write this as, from the left, the limit as x approaches 1 from the left of f of x, it looks like that equals 4. From the right, the limit as x approaches 1 from the right, looks like we're approaching -2 of f of x. Got to have that f of x equals -2. If this was like an AP open response question, you could establish those two statements and you could say, therefore, that is a symbol there that means therefore, the limit as x approaches 1 of f of x does not exist. Great job. Think about any questions you had and leave them at the last question response.